Okay, good afternoon and welcome to our second class on probability and statistics. What we'll be talking about today is discrete distributions. Okay, so the learning outcome for this study is we will define what a random variable is and differentiate a discrete distribution from a continuous distribution, and we will determine the mean, variance, and standard deviation of a discrete distribution. We also solve problems involving binomial distributions using the binomial formula, and we will solve problems using the Poisson formula to solve Poisson distribution problems. Okay, so this is just what we're going to discuss. So in the first place, what is a random variable? So as the name suggests, it's a variable that its outcomes are uncertain, or it contains outcomes of a chance experiment. A chance experiment is a kind of experiment that the outcomes are uncertain. So an example is when you're about to toss a coin as an experiment, you don't know whether the head or the tail will appear. So that one is a chance experiment. An example, suppose that you sit at a toll booth and within 30 minutes interval, you want to observe the number of cars that come to the toll booth. You know, this experiment, you don't know the number of cars that will actually come. It could be that 0 cars will come, 1 car, 2 cars, and so on. You don't know the number, so this is a chance experiment. And so the numbers that appear, either 0, 1, 2, these are random variables. So it could be 0, it could be 1, it could be 10. These are all what? Random variables, because you don't know which one will end up being the results. And it is discrete because, you know, when you are observing the number of cars coming, under no circumstances will you say that you are observing you observe 1.5 number of cars. So these numbers are discrete because they take precise value, not with decimal places. So it is discrete. It is discrete because it takes numbers which are precise without decimal places, and it is random because we don't know the outcome of the experiment until it is performed, and it is a variable because it has the tendency to change. I think we know this one from our previous lessons. Okay, so when we are running such an experiment, in that we sit at a toll booth and expect and look at the number of cars that will come within, let's say, a certain period of time. There's a way that we can use to calculate the mean number of cars that will appear. And the mean number of cars that would appear is also called the long run average of occurrences. So that's the average of occurrences, and it is called mu. Remember, mu is what we gave in our statistics class as the population parameter, or the population mean. And it is also called expected value of x. Expected value of x, and it is given by the summation of x dot the probability of x. So E of x is what? The long run average, or the expectation of x, or the mean of x, and x is an outcome. So if we get 4 cars appearing within that 30 seconds interval, then x is an outcome. P of x is the probability of getting x within that time. So the probability of that outcome. So let's say if x is 4, the probability of getting 4 cars within that 30 seconds period has been expressed in this. So these ones can be explained simply by looking at this example. So let's say discrete distribution occurrences of daily crisis. Let me use this one just as accident. So let me use it as accident, which is a common term in our language. So let's say number of accidents on a particular road, that is it, number of accidents on a particular road. So the probability that there will be 0 accidents has 0.37 probability on that road. And when there is 1 accident, it has 0.31 probability. 2 accidents on the road has 0.18 probability. So that road has some level of outcomes, of which any of this can be the number of accidents that can occur on that road. And these are the likely probabilities of how the accidents will occur. So when we want to follow this example, this formula, it means that the number of crises or the number of accidents is our x, which has been written here. The probability of x, so the probability of 0 accident occurring is 0.37. Probability of 1 accident occurring is 0.31. So that one has also been stated here. But if you want to find the expected value or the mean of the number of accidents, then it is what? Summation of x dot ps, or x times probability of x. So when you look at this, x times this will give us 0, which is x dot p of x. 1 times this will give us 0.31. 2 times this 0.18 will give us 0.36. And then when we sum, because the formula says what? You sum them. Sum means addition. When we add all of them, we get 1.15. So on the average number of accidents on that road in a day, because they said what? Daily prices. In a day is 1.15 prices. So this one, if you want to explain it or give inference about it, you can approximate it to, let's say, 1. But for calculation's sake, it is 1.15 accidents. The mean accidents on it is 1.15. Okay. So then if we know the mean, then we can also look at the standard deviation of the number of accidents that occur on that road, given the probabilities that we have been given here. So that one too is also giving us, this is the variance, which is sigma square, which is equal to sum of x minus mu square dot p of x. Okay, so this becomes the variance, and then we know that if the square root of a variance is what? Standard deviation. So if we take square root here and then square root here, then we get the standard deviation formula. So let's look at how we will use the same example to calculate for our variance and then our standard deviation. So remember this one from the previous page where we did this calculation that we got the average accident on the road to be 1.15. So for us to obtain this formula, we first have to take the mean, the average from each of these observations. Just like how we were calculating variance in our previous classes. So we take mu from these ones. So mu from x, mu from 1, mu from 2, and that one will give us this. And after that, we square all of them. So you can just type this on your calculator, this minus 1 minus that all squared, and it will give you this value. And when we get this value, you see that the formula has this value times p of x. So this value times p of x. So we have to multiply this value times what? P of x. And that is what has been expressed here. And we get these values. After that, the formula says we should what? Sum them. So then we add all of them. And then we get 1.41. 1.41. So the variance, which is sigma square, the summation of this, which is equal to that. But when we want to find a standard deviation, then we have to take a square root of the sigma and then get 1.9 prices. So the intervals between accidents is 1.19 accidents. Okay, thank you. I believe this one is very clear and you'll be able to solve it if you follow the procedure. Now there are types of discrete distributions that I want us to talk about. The first one is what we call the Bernoulli distribution. The Bernoulli distribution. Bernoulli distribution only looks at if you are conducting just a single experiment. it looks at whether it will be a success or it will be a failure. So it's just two stages. If it will be a success and it will be a failure. So it looks at the success probability and then the failure probability. So let's say you want to toss a coin. The coin has two faces. You want to toss it once. The probability that a head, if you are interested in head, then head is our success. So the probability that the head will appear is what? 1/2. So our probability of success is 0.5. And then our probability of failure will be 1 minus the probability of success, which will be what? Also 0.2. So if our probability of success is P, then our probability of failure will be 1 minus P. These are probabilities. They are numbers between 1 and 0. So it helps. But Bernoulli experiment only deals with just one experiment. You are doing one experiment and you are looking at the probability of what? Success and failure. So normally we determine success by 1 and then we determine failure by 0. So an example is a company is assessing how people are able to default or just a default in their investment. So it is just, you get a specific time period and then the company will say that, oh, in 2013, did we default or did we not default? So this is just 2014, one experiment. Did we default? Success. Did we not default? Failure. So it's just one experiment. Okay. So I believe we know what P is, probability of success, and 1 minus P will be the probability of failure. Okay. So let's talk about this distribution. This one is a binomial distribution. It also uses the success and the failure, the two-stage success and the failure as its outcome. But this one is not only one experiment. So binomial distribution talks about when you do, if you are interested in getting the head when you toss a coin, when you toss a coin for, let's say, 5 times, how many heads are you going to get? So that is what the binomial distribution talks about. It talks about the number of times or the number of trials of the experiment. So it has some assumptions. It said the experiment involves n identical trials. So n identical trials, that means when you toss a coin first, when you toss the same coin second, toss the same coin third. So these trials are identical. You don't toss a coin in the first and then you go and roll a dice in the second. You get it? So tossing a coin is the identical trial. And each trial has only 2 possible outcomes, as I denoted, either a success or a failure. Each trial is independent of the previous trial. And we know when we toss a coin, the fact that you got a head in the first toss doesn't mean you are going to get the head, a tail in the second toss. So they are independent. The first toss, the second toss, they are all independent. The term P and Q remain constant throughout the experiment. So their probability remains constant. So like I said, if P is success, then we denote failure by what? A Q. And Q is given by what? 1 minus P, which is the probability of failure. Okay. So this is the binomial formula. We know this is combination sign from our previous class. So n combination x, probability of success to the power x, Q, probability of failure to the power n minus x. We know that this Q is the same as 1 minus P from our previous slide. And then we know combination is given by this, n factorial, x factorial, n minus x factorial. And then we add this one to it. So the n is the number of trials, which is n. X is the number of successes desired. So if you are conducting 10, you are tossing coin 10 times, the 10 becomes what? Our n. But if you are expecting 3 heads, Then the 3 becomes our successes because we are interested in 3 heads. Then the P, as usual, is the probability of success. When we are tossing a coin, it is 50-50, so 0.5. And then 3 will be 1 minus 0.5. That is the experiment. So also the mean and the standard deviation of this experiment is given by mu, which is equal to n dot p. The mean is n dot p. That is the number of trials times the probability of success. And then the standard deviation is given by the root of the number of trials times the probability of success times the probability of failure. Okay, thank you. Let's look at this example on binomial distribution. Okay, they said the probability that a match, a match stick will break on being struck is 0.04. What is the probability that out of a box of 50, none will break? So we have a box of 50 matches. The probability that one will break when you strike it is 0.05. What is the probability that none of them will break? So this is our n is 50. Probability of success is 0.04. So that means the probability of breaking is our success, which is 0.04. Probability of not breaking, which is this probability of failure, will be 1 minus p, which is 1 minus 0.04, which is 0.96. So this is what our Q. Okay. And then, as I said, the number of experiments is what? N, which is 50. So when they said none will break, it means N combination 0. So 50 combination 0. And then our probability of success to the power 0. If you look at this part, so X is 0 because they said none will break. And then 50 minus 0. So this can be simplified, because this one is 0, we have n factorial divided by n factorial, it will cancel. Then we have 1 minus p, the Q part. This one, p to the power 0 is 1, so it will never appear again. So 1 minus p, n minus 0 will be n, so we have 1 minus p to the power n. We know n to be what? 50, and we know 1 minus p, our p is 0.4, so 1 minus p will be 0.96, and we have 0.1299. So the probability that none will break is 0.1299. Okay, let's look at the second one. It said the probability that more than 2 will break. More than 2 will break. So when we're looking at more than 2 will break, we are looking at 3 will break, 4 will break, 5 will break, 6 will break, 7 will break, up to 50 breaking. But if we want to do this calculation, it will take a very long time. But there is a way of doing this. If more than 2 will break, then it means that 2 or less will not break. Do you agree with me? If more than 2 will break, then 2 or less will not break. So we just have to find the probability of 2 or less and then subtract it from 1, and then we will get the probability that more than 2 will break. So we will look at probability that 2 or less, so probability that more than 2 will break is equal to 1 minus the probability that 2 or less will break. So 2 or less will break is equal to a probability of, 2 or less start from 0, 1, and 2. Probability of 0, probability of 1, probability of 2. We've already calculated the probability of 0 breaking in the first example, so we will not go over it. But this, we calculate the probability of 1 breaking, which is n combination 1, p to the power x, 1 minus p to the power n minus 1. So we get this. So then our n is 50. We put the 50 in. Our p is 0.04. And then our 1 minus p, which will be 0.96. And then we perform this and we get this probability. So this is the probability that 1 will break. When we look at the probability that 2 will break, the same approach, we get this probability. So the probability that 2 or more will break, like I said, is 1 minus the probability that 2 or less. The probability that more than 2 will break, sorry, is equal to the probability that 1 minus less 2 or less will break. So we add this probability to that one, and then to this one, the 0, 1, and then we will subtract it from 1, and then we will get the probability that more than 2 will break. Okay, so the C also asks us about what? The expected value, which is the mean, and then the standard deviation. And then from this formula, it is just simple. We know N is 50, P is 0.04. So if P is 0.04, then Q will be 0.96. So that is just has been NP is 50 times 0. So the expected value is 2. So this one is explained as if you are using the 50 matchsticks, the average number of matchsticks that is expected to break is 2. That is it. Okay. So, and the standard deviation has been given as this. That is the difference, the deviation among the breakages of the matchsticks. So this is also the NPQ. So 50 times 0.04 times the 0.96 will give us 1.6. I believe this one is also clear with this example. Okay, let's look at the Poisson distribution. Poisson distribution only talks about the number of events occurring within a particular time interval. Okay, so let's read this. A Poisson distribution focuses only on the number of discrete occurrences over some interval or continuum. A Poisson distribution does not have a given number of trials, let's say n. So in our previous lesson, they will not tell you that n or 50 matchsticks, but within a time interval, how many matchsticks will break. You get it? As a binomial experiment does. For example, whereas binomial experiments might be used to determine how many Kantanka-made cars are in a random sample of 20 cars. So if you are sampling 20 cars, how many of them will be Kantanka cars? So Kantanka car becomes the success, not Kantanka cars becomes the failure in the binomial case. A Poisson experiment might focus on the number of Kantanka cars randomly arriving at an automobile repair facility during a 10-minute interval. So Poisson will look at it in this way. Within a 10-minute interval, among the number of cars that approach a particular automobile repair facility, how many of them will be a Kantanka-made car? So that I think the difference is clear. Binomial is saying among 20 cars sampled at random, how many of them will be Kantanka cars? But Poisson is saying that among cars arriving at a particular facility within some 10 minutes interval, how many of them will be a Kantanka-made car? So under with the Kantanka-made aspect, the total number of cars is not known, but we know that within this interval, we want this number of cars of Kantanka cars. Okay. So the Poisson distribution is given by this formula, where you have lambda raised to the power x, exponent of negative lambda, and then x factorial. We know that the x being the number of cars that are likely to appear within that interval. So if you want the probability that 2 cars will appear, then x here becomes 2, lambda to the power 2. And then the lambda is the average run. So like there is an average value, there's a mean value for the number of cars that appear there. It has been calculated already. So all you have to, this value is given, and then the E is 2.7. So when you need the X, you just have to put the X there. The mean or the lambda will be given, you have to put it there, and then you solve the probability that 2 or 3 cars will appear at the facility given a specific time period. Let's look at this example. I think it is very much clearer for our understanding. Suppose bank customers arrive randomly on a weekday afternoon at an average of 3.2 customers every 4 minutes. So this one has been calculated by the bank that 3.2 customers appear there in every 4 minutes. What is the probability of exactly 5 customers arriving in 4 minutes interval on a weekday? So what will be the probability that 5 will appear on a weekday? So from this example, we know that our lambda, the average that we have been recording always, is 3.2. So lambda is what? 3.2. Then they said, what is the probability that exactly 5? So exactly 5, our x here is what? 5. So we can just put 5 here, then our 3.2 here, and then E is 2. So we can solve this simply as this. 3.2 raised to the power 5 factorial, and then we can perform this and get to know that if a bank average is 3.2 customers every 4 minutes, the probability of 5 customers arriving during any 1 4-minute interval is 0.114. So the probability that 5 customers will arrive at the bank will be what? 0.114. There is an extension of this question. They said the bank customers arrive randomly in a weekday afternoon. It's the same question, but they are asking us to find what the probability of having more than 7 customers in a 4-minute interval. So it's the same 4 minutes in a 4-minute interval on weekday afternoon. So still the lambda remains, or the mean remains 3.2 per 4 minutes. And then we are looking at x being greater than 7. So they said more than, what is the probability that more than 7 customers will arrive within that 4-minute interval? There is a way from the previous one. We can do it 1 minus 7 or less. If you want more than 7, we can have 1 minus 7 or less. So that one we can start with 0 arriving, 1 arriving, 2 arriving, 3 arriving, 6 arriving. But we can also continue. So if they say the solution requires obtaining x greater than 7, then we have x will be what? 8 customers arriving within 4 minutes interval, 9 customers, 10, 11, 12, 13, and so on. But the good thing is, as you solve this, the probability of more people appearing decreases, as you can see. So probability of 8 customers appearing within that 4-minute interval will be the lambda 3.2 raised to the power 8. The same, we get 0.114. We do it with 9 appearing, we get 0.004. We do it with 10. This calculation is, I think you can perform it on your calculator, you get 0.00. And then you see that as we move on, at a point in time, you realize that it becomes 0, 0, 0, 0. So this means that under no circumstances will 13 customers appear within that 4-minute interval. So we sum all these probabilities from up to down, and then we get 0.0169. So if the bank has been averaging 3.2 customers every 4 minutes on weekday afternoon, it is likely that more than 7 people will randomly arrive in any 1 4-minute period. The answer indicates that, this answer indicates that 7 people will randomly arrive in 4-minute period, only 1.69%. So 1.69% times more than 7 customers will arrive. So this is very slim. That's among all the period there, or within the 4 minutes interval, the percentage of time that 7 customers will appear is 1.69 of the time. So bank officers could use this result to help them make staffing decisions. So like the customers coming within every interval, then it can inform you the number of employees you may have. So this is the two discrete distributions that I want us to talk about. We have continuous distributions there. Maybe we'll talk about it in our next, but we have spoken about Bernoulli, Binomial, and Poisson. They are all discrete distributions. Stay safe in this COVID period, hoping we meet face to face. If there is any challenge, like I said, gather yourself. On Tuesdays and Thursdays, I'm on campus. I will have access to board and I will explain things to you. Thank you very much and have a lovely day.